Birkir Heimisson. I'm a project manager for smart grid development at Landsnet, the TSO of Iceland. Today I'm going to be talking about the wide area monitoring and how we've implemented wide area controls to improve the stability of the Icelandic transmission system. So my agenda today is first I'm going to talk about how the transmission system of Iceland looks like and the operational challenges, then over to the development of wide area controls, the methodology, testing and implementation, going through some real life examples from disturbances in our grid, and to finish up with what's next for wide area controls in Iceland. So this is Icelandic transmission system. So it's an island in the middle of the Atlantic, and it consists of these maybe 3 to 20 kV systems, which are kind of the centers of inertia in our system. And it's very weakly connected with this 132 kV ring connection. And that's one thing of problems we're having in the operation, how to deal with dynamic effects. Our load peak is about 2,400 megawatts, and 80% of that is power intensive users like aluminum smelters and some heavy users. And each kind of load unit within those industries is relatively big to the overall system. So if you are having trips of those load units, trips of some of our larger generators, it creates a very large dynamic effect and large disturbances in the grid. Another unique thing with our grid is that we are 100% renewable. 70% of that is hydropower and 30% is geothermal. But still, we consider the system as a low inertia system, not because of the generators themselves, more to the relative size of these big users in the system. And one of the things we have used through years to deal with these dynamic issues I talked about, especially with these ring connections, is special system protections, where we create islands. And the most common one is this split line I've shown here on the graph, going from here in the north down to the southeast, and splits the system into the west and east islands. And again, this is just a conventional special system protection, just using overload, overpower protections to open a breaker here on a double bus per hydro station, and in another substation here, creating these 2 islands to mitigate the response during those large disturbances, large imbalance events in our system. And about 10, 12 years ago, we started to install PMUs in our system. So here's an overview of where we have installed PMUs in the system. So we got a quite good coverage. Our communication network is quite good. And on top of that, when it comes to a control design, lots of our customers were willing to trial innovation. And the good thing about testing out these controls is that we are an islanding system, and kind of the new control were measurable within the overall grid. And again, we've used this, we started using it as a wide area monitoring system with all its kind of benefits. So we started with the control room. We have a real-time monitoring of it in the control room to look at generators, load consumers, loads, voltage profiles, and so on. And also very beneficial, of course, as many of you know, in post-fault analysis. It helps a lot on top of any other like fault recording and so on. Oscillations, very important to analyze oscillation in the system, and has been very powerful in commissioning testing of any new devices or equipment in the grid. If it's FVCs, new generators, PSS tuning, which was kind of the main reason why we started this journey with PMUs. And lately, we of course had to use it in some kind of model validation, checking our dynamical models against very accurate synchronized real-time data from the grid. But lately, to kind of tackle and mitigate with this powerful technology, how could we deal with those disturbances in the grid? We looked into the options about 6 years ago when we formed what we refer to as the smart grid group within Landsnet, and it mainly focused on wide area controls. And to begin that, we saw that all our powerful data we could gather from these PMUs, and we could use them as automatic responses in the grid. So we started to look and implement those. So if we look a little bit into how we designed it and what effects we are using. So here you can see one overfrequency event where we lose a big load, and eventually we go into islanding, split up to these west and east islands as I showed in the beginning. And this is clearly showing the effects of sparse inertia in the system. And here are the details. If we zoom into this, we see that the frequency isn't uniform all over the whole grid. We're seeing how it diverges and how it moves faster closer to the disturbances itself. And using that alongside angle differences in the grid, we can use those very, very detailed information to create some smart detection and how we could trigger wide area controls. So kind of going to the general method of it. So we looked into kind of strong regions which were unlikely to get islanded, and we started to kind of aggregate multiple PMUs within that zone. To aggregate them together is kind of averaging it out, because using a local PMU, just a rock of signal from a single PMU, it can be a really noisy and inaccurate signal. But it works as a kind of a smoothing function to aggregate those PMUs together. From each region, we can then create equivalent voltage phasor for that area, a frequency and a rock of signal for each region. Then we can add multiple regions. So at the first, we just looked at these two main regions because that was the main interest of the resources we were able to control within those regions. And then from the regions you use, you can make the system average angle. And it's just aggregating the number of regions together. On top of that, we use kind of the inertia estimates within each region for the Icelandic system, because it's very kind of flat profile. It's very constant, the day profile, so to say. So we just used a fixed number of inertia for each region, but that number can also be changed and adjusted for if the system changes drastically, or in other system, if this was implemented, it could have a real update of the inertia value of it. And from the inertia value, we can stack up the response in different thresholds. So we can ask for all the steps you have available in the response itself. And we link that, as I say, to the inertia of each region. And these schemes can adjust really quickly if there's an islanding formed. So it detects if it gets islanding, and then it changes parameter sets to the particular island where the resource is being controlled. And again, that general method allows for a multi-area scheme. So you can add as many schemes as you want. And the goal of this is, of course, to be a fast detection, and that when talking about fast, you're not talking about protection fast, but it's within half a second. So really want the response to like a kind of trigger. Maybe it's usually trigger around 200 to 300 milliseconds, but usually we're getting a response from the response providers between 500 milliseconds up to a second. Again, a locational element is very crucial in this, and from these methods I've discussed, we can clearly define where the disturbance is happening and ask for a response within that particular region. And with a stack up thresholds, we are also proportional to the disturbance, so the scheme should never overreact to a disturbance in the grid. And we refer to this usually as a response-driven control. It looks what the system is doing and responds accordingly. But on top of that, in these control schemes, we can also add site-specific logic, which we call more event-based. We can then customize completely within a smaller region or smaller control scheme if we want some additional triggering levels, if we want some other logic being run parallel to this general locational based logic. Most of this work was actually done under a European project called Migrate, which just finished in the end of last year, where most of this was implemented, but Landsnet had started a little bit prior to the project to implement those control. Here, coming to the response providers themselves, so this is overview of what we are using within the scope of these wide area protection projects, and it mainly focuses on big load consumers, the smelters. So all of the smelters, we have 3 big smelters in Iceland, all of them have implemented some kind of these load controls where we can send them signals to use the load as regulating powers. So we can ask them to both increase the load and decrease the load in a very, very quick manner. And usually for those schemes today, we have implemented 2 steps of load increase and 2 steps of load decrease of any other conventional under frequency protection or something that we had prior to these wide area control projects. Another interesting project which was done under the Migrate work was to look at a hydro station, a conventional hydro station being regulated, having the hydro being the regulating plants in the system. We managed to get a lot quicker response by implementing a wide area control on top of any other governor action. So in those cases, we give them signals when we want the maximum response from the down regulation of the plant, and then we pull the signal when we want it to stop. And we build all kinds of safety mechanisms in that as well. Also in the scope of this project, we have what we usually refer to as microgrids. That's some kind of protection scheme where we open a breaker to create islands and something like that. Or in our weaker 66 kV systems, we have some microgrid functions as well. The latest projects we've been focusing on is with the geothermal plants, both here in Theistareykir in the northeast, and also a little bit here in Reykjanes Peninsula, where we're trying to have the geothermal units react according to disturbances in the grid. In the past, geothermal plants have not been the regulating machines or units in the system, and now we're experimenting with giving them signals to either change to frequency control or having them do some fast ramp control on top of any other regulation in the grid during those large disturbances. And final one is the latest kind of consumers, the data centers. They are also we are also experimenting with them kind of controls to even if it's a load shed or if it's some kind of load control, it's also being worked out with them. A little bit into the test environment. What we've been doing in Iceland is use the data we have available, and we use a Phasor controller, which is a product from GE, alongside the Phasor Point, which is the wide area monitoring software. And in this, we're using the classical synchrophasor data, IEEE C37-118. And for the testing we did, we have this control platform. We can program any of these wide area control logic just using a standard IEC 61131 PLC logic. So the inputs to all of this is the C37 data. But this controller then, we usually use a 6150 to interact with any of the provider, if it's just giving I/O on the remote end or something like that. So it can usually we go for the 6150 GOOSE output of it. But how we tested this is we take disturbance data from our wide area monitoring system. We use it in a simulator here, where we take the C37 data and stream it to the controller as it was real data. The controller streams back kind of its calculated data and its action, but then on the other hand, it would stream out the control signal to the controllable units. And when we were doing a massive trial of this with multiple events, we implemented some kind of scripts and comparison methods to see if we were improving when we did some changes in this. So we did a run of some events, we did some changes, we ran it again and could compare it. and it turned out really good. And here's just a diagram of kind of modularity based how the control schemes work, going through some validity checking, fault detection, then aggregation phase, islanding detection. The latest one, which I'll refer a little bit later in this presentation, about the power and balance functions, and then the triggering stage before it reaches the IOs. Again, similar to 6150, we have this metadata assigned to each of the signals flowing through the whole system all the way to the IOs as well. So it carries the quality, it carries the time sync, it carries the test flag, everything. So we can fully, yeah, get the full control of the metadata to decide when to use the signal and when to not, when to trigger the IOs, implement the test flag, and so on. So it's very, very powerful, and usually this part of the design takes up probably the majority of the time. You develop your control scheme, but then to go through all the details to check all the metadata and how it's processed accordingly, it's time consuming, but it turns out in the end product for sure. A little bit into the implementation, as I said, we have these Phasor controllers, and we've gone through a decentralized design. So we want to have kind of a controller, at least within a region of the controllable resource. And then the controller usually communicates to IO unit using 6150 GOOSE before it does the conventional IO to the actual control, for instance, with the smelter to the rectifier controls, to the electrical governor in the hydro plant. But if we look to the east, for example, this is a case where we are actually load shedding fish factories, which are on curtailable load. So we have a installed capacity about 100 megawatts in these 6 locations. There we have implemented the one regional Phasor controller, which we implement with GOOSE communication down to these different locations, and we trigger according load shed really fast, at least compared to the old way we did it only with frequency protections, where we always had to wait until the event became really bad to start tripping load. Now we can detect it with these wide area controls really early in the stage and trip it way before it reaches some critical levels, for example, in the frequency. And in this particular scheme, we also implemented the site-specific logic on top of the general logic. So there we're looking at overloading into that 66 kV regional grid. So we can implement some, if there's a trip of lines or overloading of some cuts into that region, we can also trigger these load sheds according to those information, something which we were not able to do easily before. Here's another example of a smart grid project we did. This is a substation called Fitjar. There we have 4 transformers, and we actually have a data center connected in that distribution system. So here's another DSO with its buses, and this data center is connecting through actually the DSO. So not connect directly to our system. So in that case, we have implemented both with that data center because it also has part of its loads curtailable. Then we have implemented both the wide area control scheme, and we also use the 6150 based protection on top of that. So here we're looking at the protection devices for those transformers. So if you're getting start signals, if you get trip signals from any of these transformers which are supporting the grid and supporting the load behind, we are taking that GOOSE signals, of course, with higher sampling rates. The wide area monitoring data or the PMU data is 20 milliseconds refresh rate, but we can go down to at least 4 milliseconds refresh rate. So here we have implemented just a smart grid controller using RTAC from Schweitzer, and from there it implements both of these controls, and it sends the load shed signal to the data center. It also calculates accurately how much it should send from this and the different stages from a wide area control. And in this case, we have installed kind of a software-defined switch here to interact directly to RTAC units, both with a data center and another thing where we're experimenting with a geothermal plant. So we're sending pretty much a GOOSE signal directly. We're never including any IOs in between in this project. So a little bit to a network architecture or the infrastructure. Today we have a single point of failure, really. So kind of all the PMUs in the system are streaming to our headquarters at Landsnet, where we have a PDC, powerful PDC, which is called PDC9, which is able to forward the packages directly with almost no time delay back out in the field to the controllers themselves, where they take the control action. But still, it's a single point of failure. So if there's a control scheme in the east of Iceland, it has to send the data all the way to the southwest and back to the east. But even though we're doing it in a not very optimal way, we're still managing to get a PMU plus communication latency with under 100 milliseconds. This is still pretty good, but the system is kind of not robust to any maybe failures in the communication system or something like that. So we have plans of improving that even further. So we want to put up these regional aggregators or regional PDCs where all the PMUs within each region stream to those PDCs. The PDC will carry the signals still to the control room for the monitoring part, but it will also implement kind of a multitask or broadcast network between the regional aggregators and the controllers themselves. There we are both making better use of the bandwidth. We were improving the latency a little bit. Scalability and robustness with this decentralized architecture will be a lot better. And we're looking into how the next states are building this and looking into other kind of these technologies as well for such network architecture to improve those schemes even further. Okay, now to the real events. Here's an example before we implemented any of the wide area controls. So we got the data from that. Here we're talking about a trip of 180 megawatts in the southwest. With that, we get over frequency, we get a lot of power flowing to the east, and the trends are showing the frequency and one of the generators used in the current wide area control schemes and the load customer. As I said, this is an event prior to any wide area controls. So we reached, in this case, a frequency peak about 51.5 hertz. This is just the governor trying to regulate and handle the event. This is the load consumer of the smelter, and they are power electronic based, so their equipment really doesn't like excursions in the frequency and bad power quality. So of course it will oscillate according to that. But when we implement then wide area controls on this, we can see the difference. We are lowering the frequency peak. We are minimizing the time with over frequency. And here's the comparison. You see that when you're using these faster wide area control of the generator, it's working a lot faster. It's a hydro plant. It's not able to respond immediately. It will take 3 or 4 seconds before you're really seeing kind of a decrease in power, but the wicket gates of the plant have started to open very early in the stage. But because of the dynamics of the plant, you won't see it in the power output until a few seconds later. Same, here's the customer. So in this case, we were asking this particular customer to increase its loads by 30 megawatts. So of course it increases by roughly 30 megawatts, but it will still oscillate because of the excursions in the frequency, but we're still getting at a roughly 30 megawatts offset. And then it will ramp it automatically back down. And this really doesn't affect any of the production of the smelters themselves. They really doesn't notice. But this is really helpful for a grid. And one of the cases why they started to implement this was prior to any of these wide area controls. There were frequent events where the frequency got even worse, and they started tripping because of excursions in the frequency or some other protections, and that meant that maybe a full pot line was tripped, and then they had to get persons on site to get it up running again, and it was a lot more effective on the production than having to provide these short responses. Here's another event, another high frequency event where a load is being ramped down. Here we're talking about 320 megawatts of load in 1 minute being ramped really fast down. So we get, to begin with, a high frequency in the event. In this second chart, you see the flow from the west to east, sorry. And then we see the generators in the west where we want the regulating to happen. And in the end, we see the load where we're able to shed here in the east. So in this event, as load starts to ramp down, we get overfrequency in the system. We trigger in the beginning this fast frequency, and we only have one unit with using this smarter control. So we get a very powerful regulation within the region where the disturbance is really happening. But the other ones do not respond as good, and the power flow always increases until it hits these limits of overload with a special system protection. So eventually, because we don't guarantee enough regulation within this region in good time, then it will trip, and then we end up with these large excursions when the islanding happens in a grid. Again, you see that immediately when this island is created, we have gotten very aggressive government response on the other side of the system. This is not good, and that creates a very low underfrequency in the eastern system. And because of the very high underfrequency, it is detected and it trips the load, about 60 megawatts load at that time in the east, but still the frequency is reaching about 48 hertz. Despite of that response. But if you focus on if we would have had more resources within the wide area control domain, for example, we would have had these two other generators within that same plant with the same control. We had about 50 megawatts still left of regulating power if we would have the same response in that plant. And that 50 megawatt would clearly drop the overloading from the western part to eastern, and we had avoided this huge event which tripped lots of customers in the end, and tripped even units in the eastern part. So we had the opportunity to minimize the frequency a lot. In the end, I just want to show you the latest development in wide area controls. We are also looking into a more powerful methods of identifying the power imbalance. So here we're looking at regions in the northeast, and here in region 4 is a small 220 kV system with 2 geothermal generators, which we could control if they go into frequency mode or not. We can monitor the boundaries of these systems, and then we get kind of an instantaneous boundary power. But we really want to see the value of that imbalance power itself, and then we use the instantaneous boundary power with the effective area inertia and the runoff within the areas, and then we're able to a lot clearer identify the imbalance of that particular system. We refer to a paper we did in the e-session of Secret this year where we focus on that. And just a quick show on other trends. I know it's a lot going on here, and it's pretty much showing that we can use those to really quickly detect islanding and the imbalance of each island. And here you see a very high step in that event where there's a lot of load loss in the region 3 and followed by oscillations. So we clearly detect and trigger on the imbalance of the region 3. And if you look at the instantaneous power, we're seeing oscillation occurring accordingly, but we are able to filter out kind of the exact imbalance of each island, which is a powerful tool to detect. Finally, Landsnet has decided that all its new substations should be fully digital 6150 substations, and currently we have one bay being commissioned in such a way. But that kind of bold decision to go with all new substations going 6150, we have a lot on our horizon. These are all ongoing digital substation projects ongoing, and if you look like 2 or 3 years ahead, this is how it looks like. It looks exciting, but to us it looks a little bit scary because it's for us it's a new technology, but still exciting. As I said, it will open up a lot of opportunities for improved operation of the grid, further automation, further improvement of conventional protections, our protection functions, and then this adds high demand on the communications and opens up new aspects regarding that. So our conclusions, these wide area controls have clearly improved the system performance during disturbances, both for system operators, generator operators, load consumers. Again, we have a lot on our horizon regarding wide area control schemes and projects, so there's a lot to look into there, harnessing the fast response of geothermal plants, the data center, even looking into wide area adapting things. As I said, this has been done with the innovation part, with everybody running in a better grid, so we got our customers to join us on that front. But we are still looking into like a new auxiliary service where people will get paid to provide such a valuable response. And again, this new decision to build only fully digital 6150 substation, that gives us a lot of interesting options in the future with reliable and faster communication between substations, looking into routable GOOSEs, sample values, and even PMU data. So the future is interesting. So thank you for your attention, and hope you have some questions.